Geometric Physics 1, Lecture 10, Lagrangian Mechanics and the Legendre Transform. Today's reading is Marsden and Ratiu, sections 7.1 through 7.4. Frankel section 10.2 supplies the variational picture. For Lecture 11, we turn to geodesics, Kaluza-Klein and Hamilton-Jacobi. For 3 lectures, we have worked on the cotangent side. Today, we start over from the tangent side and then we join the two together. Lectures 7 through 9 built the Hamiltonian side. We had a symplectic manifold, a function h, and the equation that the interior product of xh with omega equals dh. Today we start again from the other end. The data is a function on tq rather than on t star q, and the law of motion is not a vector field. It is a variational principle. There are 4 stops. First, Hamilton's principle, where the action is an integral along a curve, and the Euler-Lagrange equations say that integral is critical. Second, the Legendre transform, which carries tq to t star q and sends a velocity to the partial of L by q dot. Third, the energy and the cotangent form. Fourth, Hyperregular Lagrangians, where the 2 pictures become one. Here is the sentence to carry through the hour. The 2 formalisms are not 2 theories. The identity capital theta L equals the pullback of theta says that all Lagrangian geometry is Lecture 8's cotangent geometry pulled back. Where the Legendre transform fails to be invertible, that pullback degenerates, and that is exactly where gauge theory lives. First, Hamilton's principle of critical action. We build the action functional and vary it, and the Euler-Lagrange equations fall out. Fix the configuration manifold Q. Fix a Lagrangian L, which is a function on TQ. Fix a time interval running from A to B and fix 2 endpoints in Q. Now form the set of all smooth curves running from the first endpoint to the second in that time. Call it the path space. It is not a finite dimensional object. It is a smooth infinite dimensional manifold. Its tangent space at a curve C is exactly what you would hope for. A tangent vector is a vector field along C that vanishes at both ends. We write it delta q and we call it a variation. The action is the map that sends a curve to the integral from A to B of L, evaluated on the curve and its velocity. Now the sentence to keep. On a manifold, you cannot write C plus S times delta q because you cannot add a vector field to a curve. A variation has to be a genuine smooth family of curves whose derivative in the family parameter is delta q. With that in hand, mechanics on Q has become calculus on the path space. One real-valued function, and we hunt for its critical points. Hamilton's principle says this. A curve is a critical point of the action if and only if, in any chart, the time derivative of the partial of L by q dot equals the partial of L by q. Those are the Euler-Lagrange equations. The proof is one maneuver. Differentiate under the integral sign along a family of curves. Use the fact that the variation of the velocity is the time derivative of the variation of the position. That is, equality of mixed partial derivatives in time and in the family parameter. You now have 2 terms. One carries delta q, and one carries the time derivative of delta q. Integrate the second by parts. Out comes the Euler-Lagrange expression, multiplying delta q plus a boundary term evaluated at the 2 ends. Now watch where the boundary term goes. It does not become small. It vanishes because we fix the endpoints, so delta q is 0 at A and at B. We define the tangent space to kill it. What remains vanishes for every allowed variation, and the fundamental lemma of the calculus of variations finishes the argument. One remark, neither half of the Euler-Lagrange expression is a tensor. Their difference is now the honest name for the principle. At a critical point, the interesting object is the second variation. It is a quadratic form built from the second derivatives of L. Take the harmonic oscillator. The second variation is the mass times the integral of the square of delta q dot minus omega squared times the square of delta q. Test it with a half sine wave over an interval of length capital T. The answer goes negative as soon as capital T exceeds pi over omega. Past half a period, the true motion is the saddle point of the action. The number of descending directions is the Morse index, which counts conjugate points inside the interval. That number is finite, So a critical point is a saddle with finitely many bad directions. The action is never a maximum either. Add a fast small wiggle and the kinetic term grows without bound. So here is the sentence to keep. Call it the principle of critical action. Minimality is a theorem about short intervals, not a principle. And the historical least action is a different functional entirely. Maupertuis and Jacobi varied the integral of p dq at fixed energy, not the integral of L dt at fixed time. Now repeat the computation without fixing the endpoints. The boundary bracket survives, and it turns out to be a one form. Define the Lagrangian one form, also called the Cartan form. In induced coordinates on TQ, it is the partial of L by Q dot times dq. Write it capital theta L. Then define capital omega L to be minus d of capital theta L. With those names, the free endpoint variation reads as follows. The integral of the Euler-Lagrange expression against delta q plus capital theta L on the lifted variation at the two ends. Expanding capital omega L gives two blocks. One carries the mixed second derivatives of L in position and velocity. The other carries the second derivative in the velocities twice. Now the sentence to keep. Compare lecture 8. There theta was p dq and omega was minus d theta, which is dq wedge dp. What we just wrote down are those same forms, with p replaced by the partial of L by q dot. That is neither coincidence nor analogy. In a few minutes, it will be the identity capital theta L equals the pullback of theta, and the Lagrangian side will have no geometry of its own. Second, the Legendre transform. It is a fiber derivative, and it is the map that ties the two pictures together. Here is the definition, and notice how little it needs. Each fiber of TQ is a vector space. So the Lagrangian restricted to one fiber can be differentiated with no connection, no metric, and no chart. And the derivative of a function on a vector space is a linear functional on that vector space. In other words, it is a covector. So define the Legendre transform, written FL. Pair FL of a velocity v with a second velocity w, and the answer is the derivative at 0 of L evaluated at v plus s times w. In coordinates, this is the familiar formula. FL sends q and q dot to q and p, where p is the partial of L by q dot. The Legendre transform moves nothing in the base, so it covers the identity on q. Compose it with the cotangent projection, and you get back the tangent projection. Now the sentence to keep. The momentum conjugate to a coordinate is not a definition anybody had to make. It is the derivative of L in the fiber direction, and it lands in t star q automatically, because the derivative of a function on a vector space is a covector. Now the proposition that organizes the whole lecture. The pullback of theta along the Legendre transform is capital theta L, and therefore the pullback of omega is capital omega L. The proof is 4 steps and no computation. Take a point v of TQ and a tangent vector w there. By the definition of pullback, evaluate theta at FL of v on the push forward of w. By the definition of theta from lecture 8, that is FL of v paired with t pi of the push forward. Now use the chain rule. The cotangent projection after FL is the tangent bundle projection tau q. So the whole thing is FL of v paired with tau q applied to w. In coordinates, tau q deletes the velocity components, so what is left is the partial of L by q dot against the horizontal part. That is capital theta L. Now the sentence to keep. This is lecture 8's proof for cotangent lifts, with one substitution. TQ has no canonical one form of its own. It borrows one from T star Q, and the lone is called L. Change the Lagrangian, and you change the geometry of TQ. 3 Legendre transforms, chosen to show the range. First, a particle in a potential. Take L to be 1/2 the mass times the speed squared minus a potential. Then FL sends Q and Q dot to Q and mass times Q dot. It is linear on each fiber and invertible whenever the mass is not 0. The Hessian of L in the velocities is the mass matrix. Invertibility of the Legendre transform is invertibility of the mass. Second, a charged particle. Add a term, the charge times the vector potential contracted with the velocity. Now the momentum is mass times velocity plus charge times the vector potential. Still a diffeomorphism because the extra term simply translates each fiber by a one form. That is, Lecture 9's fiber translation arriving from the Lagrangian side, and it is why momentum is not mass times velocity in a magnetic field. Third, a Lagrangian linear in the velocities. Now, FL does not depend on the velocity at all. Every fiber is crushed to a single point, and the Hessian vanishes identically. The important instance is the phase space Lagrangian, PQ dot minus H, whose Euler-Lagrange equations are exactly Hamilton's equations. Third, the energy and the geometry. We build the energy function and then rewrite Euler-Lagrange as a Hamiltonian equation upstairs on TQ. Two functions on TQ now, and both are built from L alone. The action function sends a velocity v to the pairing of FL of v with v itself. The energy is that pairing minus L. In coordinates, the energy is q dot times the partial of L by q dot minus L. Try it on a particle in a potential. The first term is the mass times the speed squared. Subtract L, and you are left with 1/2 the mass times the speed squared plus the potential kinetic plus potential. The minus sign in the Lagrangian has become a plus in the energy, and nobody chose that. One warning, and it matters: the energy lives on TQ. The Hamiltonian lives on T star Q. They are different functions on different manifolds, and it takes the Legendre transform to relate them. Conflating the two is the commonest source of sign confusion in this subject. Now the sentence to keep. The energy is the Legendre pairing itself, momentum against velocity minus L, written invariantly. It is built from L alone, with no choice at all about what energy ought to mean. One determinant now controls everything. Call the fiber Hessian the matrix of second derivatives of L with respect to the velocities twice. Say that L is regular at a point when that matrix is invertible there, and degenerate otherwise. Now the proposition: three conditions are equivalent at a point of TQ. First, the determinant of the Hessian is not zero. Second, the Legendre transform is a local diffeomorphism near that point. Third, capital omega L is non-degenerate there. The first two agree by the inverse function theorem, because the Jacobian of the Legendre transform is block triangular, with the identity and the Hessian on the diagonal. The first and the third agree because the matrix of capital omega L carries the Hessian off the diagonal and a zero block in the corner. Its determinant is the square of the determinant of the Hessian. Now the sentence to keep. Three statements of completely different kinds. An algebraic condition on second derivatives. A topological condition on a map. A geometric condition on a two-form. They are one condition, and everything that follows splits along it. Let the Lagrangian be regular. Then capital omega L is closed and non-degenerate, so TQ is itself a symplectic manifold, and the energy has a Hamiltonian vector field on it. Here is the theorem. There is a unique vector field Z on TQ whose interior product with capital omega L equals dE. It is automatically a second-order equation, meaning that pushing it down by the projection returns the identity, and its integral curves are exactly the lifted solutions of the Euler-Lagrange equations. Check it in 1 degree of freedom with L equal to 1/2 the mass times Q dot squared minus a potential. Then capital theta L is mass times Q dot dQ, and capital omega L is mass times dQ wedge dQ dot. Write Z with two unknown components and match. The first comes out equal to Q dot, which is the second-order condition. The second is minus the derivative of the potential over the mass, which is Newton's law. Now the sentence to keep. E applied to Z is capital omega L of Z with Z, which is 0. Energy is conserved by antisymmetry, exactly as in Lecture 7, and for exactly the same reason. Two Lagrangians carried all the way through. First, a particle in a potential on ordinary space. The Legendre transform sends the velocity to mass times velocity. The energy is kinetic plus potential. The Hamiltonian is the momentum squared over twice the mass plus the potential. And the Euler-Lagrange equation says mass times acceleration equals minus the gradient of the potential. Newton's second law is the Euler-Lagrange equation of the simplest Lagrangian there is. Second, the free particle on a Riemannian manifold. Take L to be 1/2 of the metric applied to the velocity twice. Then the Legendre transform is the flat musical isomorphism, which lowers an index with the metric. It is a diffeomorphism precisely because the metric is non-degenerate. Here, the energy equals L, and the Hamiltonian is 1/2 the squared length of a covector in the inverse metric. The Euler-Lagrange equations are the geodesic equation. Now the sentence to keep. The Christoffel symbols were not put in by hand. They fell out of one integration by parts, as the price of symmetrizing a derivative of the metric. Free motion on a Riemannian manifold is geodesic motion, and Lecture 11 takes that seriously. Fourth, hyperregularity, and where it fails. The successes take one theorem. The failures take the rest of the course. A Lagrangian is hyperregular when the Legendre transform is a global diffeomorphism from TQ onto T star Q. In that case, define the Hamiltonian to be the energy composed with the inverse Legendre transform. In coordinates, that is the recipe everybody learns. Solve for the velocity as a function of position and momentum. Then the Hamiltonian is momentum times that velocity minus L evaluated there. When you differentiate, the two terms carrying the derivative of the velocity with respect to momentum cancel against each other exactly. That cancellation is the Legendre transform. Regular is local, hyperregular is global. The gap between them is real. Take L to be the square root of 1 plus q dot squared on the line, it is regular everywhere. Yet its Legendre transform maps the whole line onto an open interval only. Regularity buys a local Hamiltonian description. It does not buy you all of T star Q. Now the sentence to keep. Notice which way the definition runs. The Hamiltonian is derived from L and the Legendre transform and nothing else. There is no separate postulate that the Hamiltonian is the energy. The Hamiltonian is the energy, read in the coordinates, the Legendre transform provides. Now the theorem that closes the circle. Let L be hyperregular and let H be the energy composed with the inverse Legendre transform. 3 conclusions. First, the Legendre transform pulls theta back to capital theta L and omega back to capital omega L. Since it is a diffeomorphism, it is a symplectomorphism. Second, it carries the Lagrangian vector field to the Hamiltonian one. The push forward of Z is XH. Third, a curve solves the Euler-Lagrange equations if and only if its Legendre image solves Hamilton's equations. The first part we proved 2 sections ago. The second uses one general fact about symplectomorphisms. Pull a Hamiltonian back along a symplectomorphism, and the vector field of the pulled back function is the pullback of the vector field. The proof is 3 equalities and then cancelling a non-degenerate form. Apply it here, noting that H composed with the Legendre transform is the energy. It runs backwards too. A Hamiltonian is hyperregular when its own fiber derivative, in coordinates the partial of H by P, is a diffeomorphism. Then the 2 fiber derivatives are inverse to each other. Hyperregular Lagrangians and hyperregular Hamiltonians are the same list, read in 2 directions. Now suppose the Hessian is singular, with constant corank R. 2 things happen at once. The image of the Legendre transform is no longer all of T star Q. Locally it is cut out by R equations, and those are the primary constraints. And the Legendre transform is no longer injective. Its fibers have dimension R, so whole families of velocities share a single momentum. You might expect the energy to be lost in that collapse. It is not. Here's the proposition. The energy is constant on the fibers of the Legendre transform, so the Hamiltonian is still well defined on the image. The proof is one line. Differentiating the energy along a fiber direction gives the Hessian contracted with that direction, and the fiber directions are precisely the kernel of the Hessian. Now the sentence to keep. So nothing is lost, but the Hamiltonian is determined only on the constraint set. Extending it off that set costs are arbitrary functions, and that arbitrariness is not a defect of the method. It is the gauge freedom of the system. Lecture 12 turns this into Dirac's algorithm, first class and second class constraints, and the constraint submanifold with its induced form. The example everybody should meet. Take Minkowski spacetime in any parameter along the world line. Let L be minus mass times the speed of light times the square root of minus the metric applied to the velocity twice. The action is then the proper length of the world line, and it does not care how that world line was parametrized. Reparametrization invariance is fatal to regularity, and you can watch it happen. The Lagrangian is homogeneous of degree 1 in the velocity. So by Euler's relation, FL of the velocity paired with the velocity is L itself. Subtract, and the energy vanishes identically. Also, FL is unchanged when you rescale the velocity, so the velocity lies in the kernel of the Hessian, and the Legendre transform crushes every ray to a point. The image is the mass shell, one primary constraint, and the whole dynamics is generated by it. Now the sentence to keep. Fix the parameter to be coordinate time, and you recover the familiar relativistic Lagrangian, which is regular. So the degeneracy was never in the physics. It was the price of writing the theory without choosing a frame. A vanishing Hamiltonian is the signature of a theory whose time coordinate is itself a gauge choice. Now the general statement due to Noether. This is her second theorem, not the famous one. Suppose the action is invariant under a symmetry whose parameters are arbitrary functions of time. Then the Euler-Lagrange expressions satisfy identities. They are not independent, and the Hessian is singular. A local symmetry forces degeneracy, always. The catalog is short, and it is everything. The relativistic particle gives the mass shell constraint. Electromagnetism, with the freedom to add a gradient to the potential, gives a vanishing momentum component, and then Gauss's law. Yang-Mills gives the same with the Lie algebra index. General relativity gives the Hamiltonian and momentum constraints. For electromagnetism, the mechanism is one line. The Lagrangian contains no time derivative of the time component of the potential because the field strength is antisymmetric. So its conjugate momentum vanishes identically. There is no equation of motion for it because it is not a degree of freedom. Now the sentence to keep. Every fundamental theory we have is degenerate. Hyperregularity is a convenience of textbook examples. Lecture 12 does constraints properly. Quarter 2 does gauge theory, where the constraint surface and its quotient are the whole subject. And Lecture 19 shows the Gauss constraint is a momentum map. 7 things to carry away. 1. The action is an integral of L along a curve, and solutions are critical points. Euler-Lagrange comes from one integration by parts. The boundary term dies because the variation vanishes at the ends. 2. Critical, not least. Past the conjugate point, the second variation goes negative and the oscillator turns saddle. 3. Keep that boundary term, and it is the Cartan form, the partial of L by Q dot times dq. Capital omega L is minus d of it. 4. The Legendre transform is the fiber derivative. P equals the partial of L by Q dot. Capital theta L is the pullback of theta, and capital omega L the pullback of omega. 5. The energy is FL of V paired with V minus L. The interior product of Z with capital omega L equals dE is Euler-Lagrange, and the energy is conserved by antisymmetry. 6. Non-vanishing Hessian, local diffeomorphism, and non-degenerate capital omega L are one condition. Hyperregular means a global diffeomorphism, and then the two pictures agree, form for form and curve for curve. 7. Degenerate Lagrangians give constraints, and the extension ambiguity is gauge. For Lecture 11, the free particle on a Riemannian manifold taken seriously, geodesics as a Hamiltonian flow, the Jacobi metric, Kaluza-Klein, and Hamilton-Jacobi.